Hello everyone and welcome to day 5 of derivatives. Good news, we're getting almost to the end of the memorize and do by hand plug and chug kind of problems. But we're going to look at the derivatives of natural log and exponential functions with different bases. Of course, not having a base of 1 because then we would not have an exponential function. So the derivative of ln of x, 1 over x, memorize it. Derivative of e to the x is e to the x. The derivative of a to the x is a to the x ln of a. Now with this, you can also have the chain rule, hence why we did this lesson after chain rule, because you can have the ln of a different function. So when you have the ln of a function, ln, 1 over the function, because we keep the inside the same, so 1 over it, times the derivative of the inside. Same thing with e to the f of x, if we had a function in with e. E to the f of x, kept the inside the same, derivative of e is just e to the x. So e to the inside multiplied by the derivative of the inside. And same with the power function of different bases. A to the f of x times ln of a times the derivative multiplied by the derivative of the inside. So let's do some examples here. So we've got ln. So this is our main function of 5x. So the derivative of ln is 1 over x, but we're going to keep the inside, 1 over f of x, multiplied by the derivative of the inside. Derivative of inside is 5. Now when we rewrite that out, you get 5 over 5x, which is just 1 over x. E to the negative 2x, the derivative of that. E to the negative 2x is just e to the negative 2x, multiplied by the derivative of the inside, negative 2. We rewrite that one of two ways, negative 2 e to the negative 2x. But we don't really like negative exponents, so we're going to negative 2 all divided by e to the 2x. And again, why? The negative exponent moves what it's attached to the denominator. And the last one, 4 to the x. Well, if we look up here, we remember that we're going to get 4 to the x multiplied by ln of the base, which is 4. The derivative of x is just 1, so we don't need to do a multiplied by 1 there. And there's our answer. Last two, of course I throw in some trig functions here. The derivative of tangent is secant squared x, so secant squared inside ln of x, multiplied by the derivative of the inside, 1 over x. And so we're going to get secant squared of ln of x, all divided by x. Do not even think for a minute here that we can cancel these x's. This is of ln of x, and we cannot cancel it. So that's our final answer. And for the last one on the page, cosine, derivative of cosine is negative sine. Keep the inside the same. Multiplied by the derivative of the inside. The derivative of the inside is e to the 3x, so e to the 3x, because e is the derivative of e is the same thing, multiplied by the derivative of 3x, 3. Negative 3, e to the 3x, sine e to the 3x. Done. Why don't you guys try, we're going to need to use difference quotient here, the quotient rule, not the difference quotient, my fault. Quotient rule here. So try those two, and then come back. So hopefully you guys got these answers. Negative 4 to the cosine of x multiplied by sine x ln of 4. With this one, quotient rule, as I said before, the derivative of e to the x is e to the x. Ln of x is 1 over x. Low d high minus high d low, all over low squared. We have a complex fraction here. So if you messed up, it's most likely right here. We have a complex fraction, so we need to find a common denominator. The common denominator, if you want to think of it, these are all over 1. And therefore, you have an x in the denominator here. We need to multiply this by x and this by x. And there, or x over x. But then the denominators all cancel. So we have x ln of x, e to the x minus e to the x. We both have an e to the x here. We can factor an e to the x out if you wanted to. And then an x ln of x squared. Either one of these, just to know, are correct answers. The last two here for this page. Ln is 1 over, of course now it changes colors when I don't want it to. Cosine, I have a bunch of different colors here. E to the 6x, 1 over all of that. That's where the derivative of ln comes into place. Multiplied by the derivative of the inside. The derivative of cosine, negative sine. Keep the inside the same. Multiplied by the derivative of the inside. E to the 6x. Keep the inside the same. Multiplied by the derivative of the inside. 6. Wow, so let's try to figure this out. Equal sign there. So we're going to get negative 6 e to the 6x multiplied by sine e to the 6x all over cosine e to the 6x. Well, right here, hopefully you guys can see this. Sine e to the 6x, cosine e to the 6x. What does that become? Sine over cosine? Tangent. And so we're going to get here negative 6 e to the 6x tan e to the 6x. The cosine, sine over cosine is tangent, so we can just rewrite it as tangent e to the 6x. Done. Here we've got x multiplied by e tan squared of 3x. Why don't you guys try to pause this and do this on your own. And so hopefully, guys, you got this. Let me just explain what I did. I did the first function then being multiplied by the second function. That's in the black writing. And the purple writing is the derivative. Well, the derivative of x is 1. The derivative of e tan squared 3x is up in the red here. I said the derivative of that equals e to the tan squared 3x. Derivative of e to anything is e to anything. Multiplied by tangent squared of 3x. Bring the 2 out in front. 2 tan 3x. Multiplied by the derivative of tangent, which is secant squared 3x. Multiplied by the derivative of 3x, which is 3. I rewrote that, combining the 2 and the 3. So 6e to the tan squared 3x multiplied by tan 3x multiplied by secant squared 3x. Wrote that in purple down there. I then did the first times the derivative of the second plus the second times the derivative of the first. Well, anything times 1 is just 1. So notice that the last step that we could do here, if we wanted to, is see that we have 6e to the tan squared 3x, or e to the tan squared 3x and e to the tan squared 3x here. So the last step that we could do is pull out an e to the tan squared 3x, then multiply that by x, 6x, excuse me. Let's try that again. 6x tan of 3x secant squared of 3x plus 1. Right now, the idea of factoring is not necessarily important. It will become later on. So being able to see that you can take out an e tan squared of 3x of each term is important to see. Not exactly right this minute, but will be later on. The last one that we have here is the derivative of ln of 5x squared over square root of 5 plus x squared. Now there's good news and bad news for you on this one. There is an extremely long way to do it, and there's a shortcut version. Since we're on a video, you guys, I'm going to write out the long version right now. You're just going to see it pop up. That's the way that would take you forever. Give you the right answer, but take you forever, and then I'll show you the shortcut way. So here is the extremely long way to do it. What I did was took the derivative of ln, 1 over all of this, so it's 1 divided by all of that. That's actually, that divided by 1 there, don't worry about. It's my mistake from doing it. Multiplied by low d high minus high d low, all over low squared. I did a bunch of common denominator stuff here, kept going. What the key thing here was that I did 1 over all of this. So 1 divided by that fraction, you multiply by the reciprocal, so I flipped it. We had x to the 5 plus x squared to the 3 halves here. You have to the 1/2 divided by 3/2, you're only left with 1 in the denominator. And then I, right here, I factored out a 5x and canceled 5x's. So what I was left with was x squared, took a 5x out, plus 10, took a 5x out there, divided by, it's raised to the 3/2, but when I had a 1/2 here, subtracted them, was left with just 5 plus x squared, was left with an x there, and I distributed. So this is the long way. You can look at it if you want, but I'll show you the short way right now. So when we use the natural log, when we find the derivative of natural log, we can also say, using natural log properties, that the ln of a quotient is equal to the ln of 5x squared minus ln of square root of 5 plus x squared. Well, why is this going to make it easier for us? Well, now we have the derivative of two separate things. So we get the derivative of ln of 5x squared, which is 1 over 5x squared, multiplied by the derivative of the inside, 10x, minus the derivative of 1 over ln of ln, so we're 1 over square root of 5 plus x squared, multiplied by the derivative of the square root of 5 plus x squared, as I said last video, 1 over 2 square roots of 5 plus x squared, multiplied by the derivative of the inside, 2x. Well, notice what we get here. The 10 and the 5 become a 2. X over x squared over x minus, these 2's cancel, so we're left with an x in the numerator. Square root of 5 plus x squared times the square root of 5 plus x squared, just 5 plus x squared. Now you're sitting here going, well, that does not look like this. Well, let's make it look like that. We can find a common denominator, so we're going to do 2 parentheses 5 plus x squared minus x squared all over 5x plus x cubed. And you'll notice here when we distribute that, we get 10. 2x squared minus x squared is just minus x squared over 5x plus x cubed. Hey, does that look now more familiar? X squared plus 10 over 5x plus x cubed. X squared, what did I mess up with it? 10 minus now. Yeah, I just can't add. 2x squared minus x squared is a positive x squared. So there we go. And now it looks the same. So, shortcut way, knowing the properties of logs makes this problem a whole lot easier. Make sure you know that rather than taking the 15 minutes it took me to write this out and figure out where I made mistakes, because it's easy too. So, shortcut way, much easier. And the joke of the day, why are obtuse angles so depressed? Because they are never right. Ha ha ha. See you guys in class.